In this video, we're going to talk about carbon-13 NMR spectroscopy. Now, what you need to know is that 99% of all the carbon atoms found on Earth consists of this isotope, carbon-12. Carbon-12 has no nuclear spin, and the reason for this is because the number of protons and neutrons in its nucleus is even. Carbon-12 has 6 protons and 6 neutrons. 6 plus 6 adds up to 12. Now, a small amount of these carbon atoms, approximately 1%, consist of another isotope, carbon-13. Now, carbon-13 has nuclear spin because the number of particles in its nucleus is odd, it's not even. It has 6 protons and 7 neutrons. So therefore, this particular isotope will be sensitive to an NMR spectrometer. So thus we have carbon-13 NMR spectroscopy. Now let's look at the chemical shifts that we have here on the board. The highest is of the carbonyl group. A carbon that's double bonded to an oxygen atom will have a chemical shift between 150 and 220. So these include the aldehydes, the ketones, the carboxylic acids, the esters, and the amines. Next up, we have the alkene double bond, which is between 100 and 150. And the same is true for the benzene ring. It's typically within 100 and 150 parts per million. Alkynes and a carbon that is singly bonded to an oxygen atom will appear between 50 and 100. Now this could be an ether, it could be the CO bond of an ester, but it's going to show up in that region. And then we have the halogens and amines. They're close to 50. Sometimes they could be around 40, sometimes they could be around 60, but usually around 50-ish, they tend to show up a lot. Now, finally, on the right, we have the sp3 carbons, which exist between 0 and 50. So you have the methyl groups, the methylene groups, and the methine group. They will show up in that range. So now let's work on some examples. So here we have 2-butanol, and we have the carbon-13 NMR spectrum that corresponds to it. So let's match every carbon in this molecule with the appropriate peaks that we see on the graph. If you want to pause the video and try it yourself, feel free to do so. So there's 4 different carbon atoms, which corresponds to 4 different signals. So let's call this carbon A, B, C, and D. So which one corresponds to the signal that's just below 70? Is it carbon A, B, C, or D? What would you say? Now this carbon is attached to an oxygen, so we have an alcohol. And if you recall, the CO bond for an ether, an ester, or an alcohol is between 50 and 100. And so we see that at approximately 69. And so therefore this will correspond to carbon B. Now all of the sp3 carbons that's not attached to anything special, as you can see, they're less than 50. But which one is which? What do we do at this point? Here's what we need to understand. A carbon atom that is attached to an electronegative, let's say an oxygen atom, is going to have a high chemical shift. It's going to appear downfield in the graph. Now this methyl group is very far away from the oxygen. It's 2 carbons away from the carbon that has the oxygen. So therefore, we should expect that it's going to be upfield. It's the most shielded carbon. And it is. This is going to be signal D, which has a chemical shift of approximately, I'm going to write it in red, 10. And the chemical shift for the CH group, that was about 69. Now, the methyl group and the methylene group, they're equally distant from the carbon with the OH. So at this point, which one will have the higher chemical shift? Is it carbon A or carbon C? What would you say? Now this carbon, carbon C, is a secondary carbon, and carbon A is a primary carbon. If you study many examples, you'll find that secondary carbons tend to have a higher chemical shift than primary carbons in C-13 NMR spectroscopy. But now there's more to it than that. But for now, this will suffice. But keep this in mind. Carbons in the interior of a carbon-carbon chain tend to have a higher chemical shift than the carbon atoms at the end. And that's pretty consistent. So it turns out that carbon C is the one that appears around 32. And carbon A is the signal that appears approximately around 23. So keep that in mind. Carbon atoms in the interior of an alkane chain, or it could be a different functional group, tend to have a higher chemical shift than those at the end. Now let's consider our second example, which is 2-methylbutane. So if you want to, pause the video and match each carbon atom with the signals that we see here. So notice that we have a total of 4 signals in this graph, but we have a total of 5 carbon atoms. That means 2 carbons are equivalent to each other. And we can see that these 2 methyl groups are equivalent. So we have 4 different carbon atoms. So let's call this carbon A, carbon B, C, and D. Now here's a question for you. Which carbon atom will have the lowest chemical shift at 12? And which one will have the highest chemical shift at 32? What would you say? Now you might be inclined to think that the one with the lowest chemical shift will be the primary carbon. And for the most part, you would be correct. But notice that we have 2 different types of primary carbons. Here, this methyl group is primary, and so is the methyl groups that corresponds to carbon A. So which one will have this signal? Carbon C is secondary, carbon B is tertiary. Now you might be inclined to think that the tertiary carbon will have the highest chemical shift. In this example, it turns out that the secondary carbon has the highest chemical shift. That's signal C. And the tertiary carbon has a chemical shift at 30. So in this case, the secondary carbon has a higher chemical shift than the tertiary carbon. Now you might be wondering, why is that? I'll give you a hint. The key is not to focus on the carbon you're analyzing, but on the adjacent carbon atoms, because it is the adjacent carbon atoms that will create a shielding or de-shielding effect on the carbon that you're analyzing. And we'll talk more about that later. Now, these 2 signals, the remaining 2, has to represent the 2 different primary carbons, carbon A and carbon D. But which one? Now, there's a way that you can tell the difference between the 2. Notice that there's 2 carbon atoms that correspond to signal A. So therefore, we should expect that the peak should be taller, which we do see that this peak is taller than the rest. And so this corresponds to signal A, which means the other one corresponds to signal D. But if these are both primary carbons, why does signal A has a significantly higher chemical shift than signal D when they're both primary? And once again, you need to look at the adjacent carbon atoms. And so let's talk about that. Right now, we're going to discuss a system that will help us to determine which carbon atoms will have a higher chemical shift and which ones will have a low chemical shift. Now, it's just a score system, and it's very useful when dealing with sp3 carbon atoms. And generally speaking, it usually works. You might find some exceptions, but for the most part, the results are pretty consistent. So let's look at carbon D. Now focus on the adjacent carbon. Carbon D is attached to a secondary carbon, so we're going to give it a score of 2. Now carbon A is attached to a tertiary carbon. So we're going to give it a score of 3. And so using this system, we could see why signal A has a higher chemical shift than signal D. Now, looking at the tertiary carbon, carbon B, it's adjacent to a primary, another primary, and a secondary carbon. So 1 plus 1 plus 2, that's going to be a 4. Now, if we look at the secondary carbon, it's adjacent to a tertiary carbon and a primary carbon. 3 plus 1 is 4. Now, these two have an equal score. And so when you get to a situation like this, you can't really tell them apart. As you can see, they're pretty close here. But if the score is different, the chemical shifts will be significantly different, that you can tell them apart. Now in this example, we have 2-methylpentane. So go ahead and assign the carbon atoms to the chemical shifts that we see in the spectrum. So first, let's identify the carbon atoms. These two methyl groups are equivalent to each other, so we'll call it carbon A, and then B, C, D, and E. So automatically, because there are two methyl groups corresponding to signal A, we know it's going to be the tallest peak. So it's going to have a chemical shift of approximately 23. Now what about the rest? Well, we know E, the other primary carbon, has to be the one with the lowest chemical shift. So that's going to be the signal of about 14. To distinguish the others, we need to use basically that score system that we talked about a few minutes ago. So let's begin by identifying each carbon atom as either primary, secondary, or tertiary. So we know the signals for, or the carbon atoms that correspond to signal A is primary, and carbon E is primary. D and C are secondary carbons, and B is a tertiary carbon because it's attached to 3 other carbon atoms. Now starting with signal E, this carbon is attached to a secondary carbon, so we're going to give it a score of 2. Now for signal A, that carbon is attached to a tertiary carbon, so it's going to get a score of 3. And so we can see why signal A has a higher chemical shift than signal E. Now looking at signal D, it's between a secondary carbon and a primary carbon, so it has a score value of 3. Now for carbon C, it's between a tertiary and a secondary carbon, so we're going to give it a score value of 5 because 3 plus 2 is 5. Now for carbon B, it's adjacent to a primary, and a secondary. 1 plus 1 plus 2 is 4. So it's going to have a score value of 4. So if we look at carbon A and carbon E, both are primary, but because carbon A has a higher score value, it has a significantly higher chemical shift, 23 compared to 14. Now, which one do you think is the one with a signal of 42? This is going to be carbon C because it has the highest score value of 5. Next up is carbon B because it has a score value of 4. And then by default, this has to be carbon D. Now notice that A and D are close to each other. And it makes sense because they have the same score value. So you can't really tell which one is going to have the higher chemical shift, even though D is secondary and A is primary. So sometimes a primary carbon can have a higher chemical shift than a secondary carbon. Carbon B is a tertiary carbon and carbon C is a secondary carbon. So sometimes a secondary carbon can have a higher chemical shift than a tertiary carbon. So carbon B has a signal of 28 and D has a signal of we'll say 21. But notice that the score system is pretty consistent. Because carbon C has the highest score, it has the highest chemical shift of 42. Next up is carbon B with a score of 4, which has the second highest chemical shift of 28. These two have the same score, so their chemical shifts are very close. And finally, carbon E has the lowest score, so it has the lowest chemical shift. And that technique is very useful for ranking the different carbon atoms when dealing with alkanes in carbon-13 NMR spectroscopy. Let's work on our fourth example. The C-13 NMR spectrum of pentane shows 3 signals with chemical shifts of 14, 23, and 34 parts per million. Match the carbon atoms with their respective chemical shifts. So let's begin by drawing pentane. Now first, let's determine the different types of carbon atoms that we have. Due to symmetry, the 2 methyl groups on the left side and the right side, they're going to be identical. They have the same exact chemical environment. And here is the line of symmetry. So therefore, these 2 carbon atoms will be similar, and carbon C will be in the middle. It will be different from the rest. Now, let's determine the types of carbon atoms that we have. Carbon A are primary. Carbon B, they're secondary carbons because they're attached to 2 adjacent carbon atoms. And carbon C is also a secondary carbon atom. So now let's calculate the score for each different type of carbon. So for carbon A, it's adjacent to a secondary carbon. So let's give it a score of 2. Carbon B is adjacent between a primary and a secondary. So 1 plus 2 is 3. And carbon C is next to 2 secondary carbons. 2 plus 2 is 4. Now, since carbon C has the highest score value, it turns out that it has the highest chemical shift, in this case of 34. Carbon B has the second highest, which is 23, and carbon A is going to have the lowest. And you could look this up. If you type in the C-13 NMR spectrum of pentane, you do a Google search, and if you look at chemicalbooks.com, they'll have those values. So that's it for this example. Try this one. So this time it's 3-methylpentane, and it has 4 signals with chemical shifts of 11, 19, 29, and 36 parts per million. So let's begin by drawing pentane, and let's put a methyl group on carbon 3. So just like before, let's identify the different types of carbon atoms that we have. So here is the line of symmetry. So this is going to be carbon A, B, C, and D. So we have 4 different types of carbon atoms, which correspond to the 4 signals that we see here. Next, let's identify each type of carbon atom. Carbon A is primary, carbon B is secondary, C is tertiary, and D is primary. Now let's focus on the score values. So carbon A is adjacent to a secondary carbon. It's going to have a score value of 2. Carbon D is adjacent to a tertiary carbon. It's going to have a score value of 3. Carbon B is between a primary and a tertiary carbon. So 1 plus 3 is 4. And carbon C is adjacent to a secondary, another secondary, and a primary. 2 plus 2 plus 1 is 5. So based on this score system, carbon C is going to have the highest chemical shift of 36. Carbon B is next. It's going to have a chemical shift of 29. And then carbon D has a score value of 3, so the chemical shift will be 19. Carbon A has the lowest score value of 2, which means the chemical shift is going to be 11. Earlier in this video, we said that Alcohols, ethers, esters, their CO bonds have a chemical shift between 50 to 100. And then we grouped the amines with halogens such as chlorine and bromine to be close to 50. So we're going to talk about that in this case. So first, here we have, this is going to be 1-hexanol. And the chemical shift for the carbon that is attached to the OH is about 63 for this example. Next, we have an amine, and the carbon that is attached to the amine has a chemical shift of about 42. Now let's compare that to 1-chlorohexane. The chemical shift for that carbon with the Cl is 45. And then for 1-bromohexane, the chemical shift is 34. And finally, for 1-iodohexane, the chemical shift is very, very low. It's 7. And we could see why that's the case. Iodine has a relatively low electronegativity value compared to the other elements on this page. According to Wikipedia, oxygen has an electronegativity value of 3.44, and nitrogen is 3.04. Chlorine is a little bit more electronegative than nitrogen. According to Wikipedia, it's 3.16, and bromine is 2.96. And for iodine, it's 2.66. So we could see that based on these molecules, electronegativity plays a role in the chemical shifts of the carbon that is attached to the electronegative atom. So the CO bond usually has a higher chemical shift than the CN bond. And the CCl bond, or the carbon attached to the chlorine atom, typically has a higher chemical shift than a carbon that's attached to a bromine atom, and that usually has a higher chemical shift than a carbon atom attached to an iodine atom. So those are some things that you want to keep in mind. Here's another question for you. Which carbon atom will have a higher chemical shift? Carbon A or carbon B? Both of them are attached to a chlorine atom. What would you say? Well, because the functional group is the same, we need to use the score system to determine the answer. So carbon A is adjacent to a secondary carbon, so we're going to give it a score of 2. Carbon B is between a secondary and a primary carbon, so we're going to give it a score value of 3. Because carbon B has a higher score value, it's going to have a higher chemical shift. It turns out that carbon B has a chemical shift of 60, and carbon A has a chemical shift of 45. So keep this in mind. When a carbon atom is in the interior of a chain, it usually has a higher chemical shift than the carbon atoms at the end of a chain. So based on that, which of these two carbon atoms is going to have the higher chemical shift? This one is at the end, this one is in the middle. It's going to be the one in the middle. So the primary carbon has a chemical shift of 26. The secondary carbon has a chemical shift of 34. Now, between the primary carbon on the right and the primary carbon on the left, which one is going to have the higher chemical shift? This one is closer to the carbon with the chlorine atom, so it's going to be more deshielded. In addition, it has a higher score value. The primary carbon on the right is adjacent to a tertiary carbon, so it's going to have a score value of 3. The primary carbon on the left is adjacent to a secondary carbon, so it's going to have a score value of 2. So therefore, we should expect that this one is going to have a higher chemical shift. And the data supports that. The value for the primary carbon on the left is 11 ppm. So you need to consider two factors: the score value and the proximity to an electronegative atom. In the case of the primary carbon here, it had a higher score value and it was closer to the electronegative chlorine atom compared to this carbon. And so both effects favored this carbon, and so we can see why it has a significantly higher chemical shift than the other primary carbon on the left. Now let's look at 1-chlorobutane. Let's compare these two carbons. Let's call it carbon A and carbon C. Carbon A has the chlorine atom, but carbon C has a higher score value. So which one will take priority? The proximity effect to an electronegative atom or the score system? Let's calculate the score values first. So carbon A, we said, has a score value of 2. Carbon C is adjacent to a secondary and a primary carbon, so we're going to give it a score value of 3. So C has the higher score value, but A has the electronegative atom. Which one is going to have the higher chemical shift? Since chlorine is a strong electronegative element, for this example, it turns out that the proximity effect is going to win out. The chemical shift for carbon C is 35. For the carbon to the left of that, it's 20. And then for the primary carbon on the left is 13. So we could see that the electronegative element had a stronger impact or a stronger effect on carbon A. Now here's another example. Instead of 1-chlorobutane, let's use 1-bromobutane for an example. Let's call this carbon A, B, C, and D. So which one is going to have the higher chemical shift? Carbon A or B? Which one is going to win out? The proximity to an electronegative element, or carbon B, which has the higher score value? Keep in mind, carbon B has a score value of 3, just like this one, and carbon A has a score value of 2. Now this is going to be a close battle, but it turns out that carbon B is going to win, but not by much. Carbon B has a chemical shift of 35, just like this one, but carbon A is 33 because bromine is not as electronegative as chlorine. And so when dealing with the proximity effect, you need to think about the strength of the electronegative atom. If it's a very powerful electronegative atom, the proximity effect will win. If the atom is not very electronegative, then the score value may take precedence. For carbon C, the score value is 21, close to this one, and for carbon D, the score value is 13, which is identical to that one. Consider this example. Let's say we have 2-iodobutane. Which carbon atom will have the higher chemical shift, carbon A or B? Because this time, both carbon atoms have the same score value. This is primary, secondary, and primary. So analyzing carbon A is adjacent to a primary and a secondary carbon, given a score value of 3. And looking at carbon B, it's adjacent to a secondary and a primary, which also gives it the same score value. So which one will have the higher chemical shift? It turns out that it's carbon B. Carbon A has a chemical shift of 32. Carbon B is 36. This is 14. And this is 29 for some reason. Now the question is why? Why is carbon B higher than carbon A in terms of its chemical shift? Now keep in mind, according to Wikipedia, the electronegativity for carbon is 2.55, and for iodine it's 2.66. So iodine is not very electronegative. And if we consider the example that we mentioned before, that is of 1-iodohexane, notice the chemical shift of the carbon that has the iodine atom on it. It's 7. The chemical shifts of a typical methyl group is usually between 10 and 15. In those two examples, it's 14. But this is unusually lower. And so iodine has the effect of lowering the chemical shift of the carbon that it's attached to. And so this is one reason why the chemical shift of carbon A, which is 32, it's less than the chemical shift of carbon B, which is 36. So now let's focus on alcohols. I'm going to give you a list of alcohols, and I want you to determine which carbon atoms that are attached to the OH group have a higher chemical shift. So I'm going to write down a few of them. Feel free to pause the video or fast forward it if you want to. Now I have 2 more examples to draw. And then the last one is going to be 3-methyl, 3-pentanol. So go ahead and rank each carbon atom. Let's call this carbon A, B, C, D, E, and F. Ethanol and 1-hexanol are primary alcohols. 2-butanol is a secondary alcohol. And this here, that's 2,4-dimethyl, 3-pentanol, that's a secondary alcohol. And the last two are tertiary alcohols. Now, tertiary alcohols don't always have the highest chemical shift. And let's see why. So let's analyze this one first. Carbon A is attached to a primary carbon, and so we're going to give it a score of 1. Carbon B is attached to a secondary carbon, and so we're going to give it a score of 2. Carbon C is adjacent to a secondary and a primary carbon, so we'll give it a score of 3. Carbon D is adjacent between 2 tertiary carbons, and so we're going to give this one a score of 6. Carbon E is next to 2 primary carbons and a secondary, so we're going to give it a score of 4. And carbon F is next to 2 secondary carbons and a primary one, and so we're going to give it a score of 5. The chemical shift for carbon A is 58. The chemical shift for carbon B, we saw that before, that's 63. And so notice that this one is higher than this one, even though they're both primary alcohols, since carbon B has a higher score value. Carbon C, 2-butanol, that has a chemical shift of 69. And then for carbon D, so that's this one here, that has a very high chemical shift of 82. And we could see that because it has a high score value of 6, even though both of these are secondary alcohols. And then carbon E, that has a chemical shift of 71. So it's a little bit more than this one. Since this is a score value of 4, that's a score value of 3, but they're pretty close. And carbon F has a score value of 73. And so this is 5 compared to 4, so we expect that this is going to be slightly higher. So notice that sometimes a secondary alcohol can have a higher chemical shift than a tertiary alcohol. And so there's many factors that you need to consider. But in summary, when dealing with alcohols, the carbon that has the oxygen typically has a chemical shift between 50 and 100. We saw a low value for ethanol, which was 58, and a high value for the one with a score value of 6, which was 82. But the carbon with an oxygen will usually be in this range, 50 to 100 parts per million. Number 6. The carbon-13 NMR spectrum is shown below for a compound with a molecular formula of C6H14O. Propose a structure for the molecule. So the first thing I would like to focus on is the functional group. We have an oxygen atom. So this could be an ether, an alcohol. It can't be an ester because that will have 2 oxygen atoms, and it cannot be a carboxylic acid. Now, could it be an aldehyde or a ketone? It can't be an aldehyde or a ketone because we don't have the carbonyl signal between 150 and 220. So that's out. Now, something we need to take into consideration is the presence of any rings or double bonds. Now, a double bond would show up between 100 and 150. So we don't have that. So we don't have a benzene ring or a double bond. Now, there's something else that we could use that will help us to eliminate some possibilities. And that is the IHD, the index of hydrogen deficiency. It's equal to 2n plus 2 minus the number of hydrogen atoms divided by 2. So N is the number of carbon atoms. We have 6 carbon atoms in this molecule, and we have 14 hydrogen atoms. Now 2 times 6 is 12, and 12 plus 2 is 14. 14 minus 14 is 0. So the IHD is 0. In order to have a double bond, the IHD has to be 1. For a ring, the IHD is also 1. And for a triple bond, the IHD is 2. So because the IHD is 0, we have no double bonds, no rings, and no triple bonds. So all of the carbon atoms that we're dealing with are sp3 carbon atoms. Now, since the IHD is 0, and as we mentioned before, there's no signal between 150 and 220, we don't have any carbonyl groups. So it can't be an ester or an aldehyde or a carboxylic acid or a ketone or an amide. And there's no nitrogen atoms here. So the only other functional groups that contain an oxygen atom are alcohols and ethers. So how do we tell if we have an alcohol or if we have an ether? Because for a CO bond, the signal will vary between 50 and 100. And notice that we have 2 signals between 50 and 100. So does that mean it's an alcohol or an ether? So if we have an alcohol, how many CO bonds do we have? An alcohol only contains 1 carbon-oxygen bond. But what about an ether? In an ether, the oxygen is between 2 carbon atoms. So an ether contains 2 CO bonds. So therefore, we should see 2 signals between 50 and 100, which we do. So therefore, the functional group that we're dealing with is an ether. So now, what type of ether do we have? How do we draw the carbon structure around it? So now, the next thing we need to focus on is the number of signals. So we have a total of 4 signals, but 6 carbon atoms. So that means we need to have some equivalent carbon atoms. So let's draw the different possible ways in which we can make an ether with 6 carbon atoms. We could put 1 carbon on one side and 5 carbons on the other side. But this would give us a total of 6 signals because all carbon atoms are different. If we put, let's say, 2 carbons on the left, 4 on the right, this won't work either because all the carbon atoms are different. So we could try an isopropyl group because by doing so, we can get two methyl groups that are identical to each other. These two carbons are the same due to the symmetry of the molecule, and these four methyl groups are identical, giving us a total of two signals. So that's not going to work. Now we can try an isopropyl group on the left and a propyl group on the right. So these two are identical, this is different, and so we have a total of 5 signals in this example. That's not going to work either. The only other way in which we can design an ether with equivalent carbon atoms is using a tert-butyl group. So we have a total of 4 carbons at this point, so we're going to put 2 on the right. So now this will be carbon A. The 3 methyl groups are identical. Carbon B, C, and D. So now we have a total of 4 carbon atoms. So this is the structure that corresponds to this particular molecule. Now let's determine where each signal goes. Now automatically we can see that this is the tallest peak. So that's going to correspond to the 3 methyl groups that we see for signal A. These 3 carbons will add up to form a large signal. Now this methyl group on the right side must be signal D, which corresponds to a chemical signal of 16. So this is 16 and this is about 23. Now carbon A is adjacent to a quaternary carbon, which gives it a score value of 4. Carbon D is adjacent to a secondary carbon. I mean, that's not a secondary carbon, but that is a primary carbon. And so it has a score value of 1. So we can see why A has a higher chemical shift than D. Now carbons B and C are both attached to an oxygen. And so we can see that the chemical shift is between 50 and 100. Now, which one is going to be higher, B or C? So now let's consider the score value for each. For carbon B, it's adjacent to 3 primary carbons, and so we're going to give it a score value of 3. Carbon C is adjacent to a primary carbon, and so we're going to give it a score value of 1. So between B and C, B has a higher score value, given that they have the same functional group. So therefore, signal B will be the one that's at 73. And signal C is, or carbon C, is going to have the signal at 57. And so that's it for this problem. Now the next functional group that we're going to talk about is the alkyne, the carbon-carbon triple bond. Now in the beginning, we placed it between a value of 50 and 100, but in practice, you'll see that most alkynes fall between 70 and 100. Now let's work on some examples. Actually, I'm going to draw this out. So here we have 2-butane, and due to the symmetry of this molecule, there's going to be 2 signals. It turns out that the signal for the carbon atom that's part of the triple bond is 75. But what do you think the signal is going to be for the methyl group? Now, most methyl groups that we've seen so far are usually around 10. We've seen them vary between 8 to 15 if there's nothing special around it. Now, this is usually the case. However, there were some exceptions where a methyl group was attached to a tertiary carbon, and we've seen values as high as 19, 21, or 23. But most methyl groups usually is around, I guess we could say 10 to 20. Maybe that's a better range. But the methyl group that is close to an alkyne, that's 1 carbon away from it, it's actually much less. In this example, it's 3. And so what you need to keep in mind is that the carbon atom, which we'll call the alpha carbon, that is basically one carbon away from the alkyne functional group, those carbon atoms tend to be lower than normal. The alkyne functional group has the effect of lowering the chemical shift of the adjacent carbon atom. And we're going to see that in a few upcoming examples. So let's consider the example of 2-pentine. So let's call this carbon A, B, C, D, and E. So there's a total of 5 signals. So which carbon will have the higher chemical shift? Carbon B or carbon C? Now they're part of the same functional group. So the only difference that we can take advantage of is the score system. Carbon B is adjacent between a primary carbon and a secondary carbon. So we're going to give it a score value of 3. Carbon C is between a secondary carbon and another secondary carbon. So we're going to give it a score value of 4. So based on that, we're going to say that carbon C has the higher chemical shift, which it does. And so the chemical shift for carbon C is 80. For carbon B, it's 75. Now what about between carbon A and D? They're both next to the same functional group, the alkyne. They're one carbon away from it. So in terms of proximity, it's the same. So in this case, because all factors are equal, we could use the score system to see if there's a difference. Carbon A is next to a secondary carbon, so let's give it a score value of 2. Carbon D is between a secondary and a primary, so we're going to give it a score value of 3. It turns out that the chemical shift of the methyl group on carbon A, it's 3, just like in the case of 2-butane. But the methylene group, corresponding to carbon D, has a chemical shift of 13. And so we can see that when everything else is equal, the one with the higher score value usually has the higher chemical shift. Now let's compare carbons D and E together. Which one will have the higher chemical shift? Now carbon E is adjacent to a secondary carbon, so it has a score value of 2. So you might be inclined to think that carbon D should have the higher chemical shift because it has a higher score value. Even though the score value is a factor, it's not the only factor to consider. So in this case, it may not always give you the best answer. We do have to consider the fact that carbon D is adjacent to the alkyne, which has the effect of lowering the chemical shift. So sometimes this carbon will be lower than this one. And for this example, that's what's going to happen. Carbon E has a chemical shift of 14. So it's a little bit more than carbon D. So because this is next to an alkyne, the chemical shift is lower. It's been lowered to the point where it's less than carbon E. Sometimes this might be a little bit more. Sometimes they might be the same. There's a lot of factors to consider. But just know that the carbon that's next to the alkyne will be lower than usual. Now let's consider an example with a terminal alkyne as opposed to an internal alkyne. Now let's see what we can learn from it. So here we have 1-hexene. Let's call this carbon A, B, C, D, E, and F. So which one is going to have the higher chemical shift, A or B? So the carbon atom that is in the middle of the chain usually has the higher chemical shift than the one at the end. There are some exceptions though, as in the case of that one. But if you look at the score value for this one is going to be 2 because it's adjacent to a secondary carbon. The score value for carbon B is going to be 1 plus 2, which is 3. It's adjacent to a primary and a secondary carbon. So B should have a higher chemical shift. And it does. The chemical shift for carbon B is 85. For A, it's 68. Now, something that I want you to pay attention to is that for internal alkynes, the chemical shift of the carbon atoms are fairly close. But for terminal alkynes, they're not as close. As you can see, they're further apart. And so knowing that, that can help you to distinguish an internal alkyne from a terminal alkyne. Now looking at the 4 remaining carbon atoms, which one will have the highest chemical shift and which ones will have the lowest chemical shift? So starting with carbon F, it's adjacent to a secondary carbon, so that's a score value of 2. For carbon E, it's between a primary and a secondary carbon, so 2 plus 1 is 3. And for carbon D, it's between 2 secondary carbons, so that's going to give it a score of 4. And for carbon C, it's between 2 secondary carbons as well, so that will also give it a score of 4. So between E and F, which one is going to have the higher chemical shift? Now, none of these are 1 carbon away from the alkyne, so we could use the score system. E is going to be higher than F, and it is. The value for E is 22, and for carbon F, it's 14. Now, between D and E, none of them are 1 carbon away from the alkyne group. So D has a higher score. D is going to have a higher chemical shift, and it's 31. Now, between C and D, the score value is the same, but C is 1 carbon away from the alkyne. Therefore, C is going to be lower than D. And the signal for C is 18. So as you can see, this is a significant drop compared to 31. Number 7. The 2 carbon-13 NMR spectrums shown below correspond to 2 different constitutional isomers of C6H10. Propose a structure for each spectrum. Now let's begin by calculating the IHD, the index of hydrogen deficiency. So the formula is 2n plus 2 minus the number of hydrogen atoms divided by 2. So in C6H10, there's a total of 6 carbon atoms, and we have 10 hydrogen atoms. Now 2 times 6 is 12, plus 2, that's 14. 14 minus 10 is 4, and 4 divided by 2 is 2. So the IHD is 2. Now keep in mind, a double bond has an IHD of 1, a triple bond has an IHD of 2, and a ring has an IHD of 1. So this could be 2 rings, it could be 2 double bonds, it could be a double bond and a ring, or 1 triple bond. So those are the possibilities that we have. Now notice that we have a signal between 70 and 80. We have 2 of them. And so this can't be a double bond because the alkenes, they exist between 100 and 150. So that is not going to be the situation here. Now, a ring won't give us a signal between 70 and 80. And we don't have any oxygen atoms, so there's no ethers or alcohols. The only possibility is the alkyne. Now, looking at this structure, would you say this is a terminal alkyne or an internal alkyne? So these 2 peaks are close to each other. So therefore, we're going to say that this is going to represent an internal alkyne. Now, these 2 peaks, we have one that's a little bit less than 70 and one that's 90, but notice how far apart they are. So because they're so far apart, this is going to represent a terminal alkyne. So alkynes can range between 50 and 100, but as we said before, typically it's 70 to 100, but sometimes you'll see some that are less than 70. Now, focusing on this spectrum on the left side, notice that we have a total of 6 signals. So therefore, we can't have any equivalent carbons. And it has to be an internal alkyne. So let's draw 6 carbon atoms where the triple bond is in the middle. So we have to put at least one carbon atom on the left of the triple bond. So we could put the other 3 on the right. So this is one possibility. Now notice what happens if we try to branch it. We'll get this possibility. Or let's say if we put 2 carbons, let me start with the triple bond. Let's say if we put 2 carbons on the left and 2 carbons on the right. So due to symmetry, we're going to have equivalent carbons. This would be the first signal. This is the second, third, fourth, fifth signal. So that's out. We don't have 5 signals. These 2 are the same. Those 2 are the same. So this will give us 3 signals. This will be 1, 2, 3, 4, 5, 6. All of them are different. And so this could work. We can't really use the tert-butyl group because, for one thing, we don't have a tall peak here. So that's another indication that we don't have any equivalent carbon atoms. Because these 2 are equivalent, we should expect a tall peak, but there is none. So right now, this is the only best possibility that we can come up with for a 6-carbon alkyne. And it turns out that this is indeed the structure for the spectrum on the left. Now let me give you the values that corresponds to the signals that we see on the graph. So this is 3, this signal is 14, the next one is 21, and then 23, and we have one at 75, and the last one is at 79. Let me see if I can space this. So looking at carbons 2 and 3, we know it has to be these 2 values at 75 and 79. So which one is going to be the one at 75 and which one is the one at 79? Carbon 2 is between a primary and a secondary carbon, so it has a score value of 3. Carbon 3 is between 2 secondary carbons, so it has a score value of 4. So therefore, carbon 3 is the one that has the higher chemical shift at 79. Carbon 2 has the lower one. Now, carbon 1, we saw multiple examples where a methyl group attached to an alkyne has a chemical shift of 3. And so this is going to be the same in this example. So that's pretty consistent. Now what about carbons 4, 5, and 6? Carbon 4 has a score value of 4 because it's adjacent to 2 secondary carbons. Carbon 5 has a score value of 3 because it's next to a secondary and a primary. And carbon 6 is adjacent to a secondary carbon, giving it a score value of 2. So what do you think the signal will be for carbon 6? Based on the many examples that we've covered so far, when a methyl group is next to, let's say, a CH2, typically the signal is around 10 to 15. And this methyl group is far away from the alkyne, so it's not really affected by it. So thus, the signal at 14 is reasonably attached to carbon 6, and it turns out that it is. Now between carbons 4 and 5, which one will be 21 and which one will be 23? Now we do expect a drop at carbon 4, and so it turns out that this one is going to be at 21 and carbon 5 is going to be at 23. They're pretty close though, even though carbon 4 has a higher score value. But because it's adjacent to the alkyne, we see the drop in the signal there. So it's a little bit lower than this one. Now let's move on to the structure on the right side. So we have a terminal alkyne, which means that we need to put the triple bond at the end. And there's only 4 signals. So we can maybe put an isopropyl group, 1, 2, 3, 4, 5, 6 carbons. But this will give us 5 signals. So therefore, we have to use a tert-butyl group. So this would be 1, 2, 3, and then 4, which is consistent with the spectrum above. And so this is the structure for this particular spectrum. Now let me give you the numbers. So this signal is at 27, this one is at 31, and this is at 67, and this is at 93. So which signal corresponds to which carbon? So looking at the two carbon atoms that are part of the triple bond, the carbon at the end is going to have a lower score value. It's going to have a score value of 2. And the carbon 2 is going to have, it's adjacent to a primary and a quaternary, so it's going to have a score value of 5. Carbon 3 is adjacent to 3 primary carbons and a secondary carbon, so therefore it's also going to have a score value of 5. And carbon 4 is adjacent to a quaternary carbon, giving it a score value of 4. So between the two carbon atoms that are part of the alkyne, this one is clearly going to be the one that's higher. So that's the one with the chemical shift of 93. And the other one is 67. Now, which one is going to be higher, 3 or 4? We really don't need to think too deeply about it because the tall peak is at 31, and that's going to correspond to the 3 methyl groups. So carbon 4 has that chemical shift. Carbon 3 has to be 27. And we could see why it's a little less than 31, because it's 1 carbon away from the alkyne group, and so we see that drop in chemical shift. Now let's talk about alkenes. The carbon atoms in an alkene have a chemical shift between 100 and 150 parts per million. And so let's consider an example. This is going to be 1 pentene. And so let's call this carbon A, B, C, D, and E. Between carbons A and B, which one is going to have the higher chemical shift? Carbon A is next to a secondary carbon. It has a score value of 2. Carbon B is going to have a score value of 3. This is primary and this is secondary. Carbon C is between 2 secondary carbons, so that's a score value of 4. And then for D, it's between a secondary and a primary. That's a score value of 3. And for E, it's attached to or adjacent to a secondary carbon, giving it a score value of 2. So let's compare these two because they're part of the double bond system. Carbon B is going to have a higher chemical shift, and the value for it in this example is 139. For carbon A, it's 114. So it's between 100 and 150, as we can see here. Now, carbon C, D, and E, we can rank them based on the score system. Carbon C is going to have the highest chemical shift, 36. Carbon D is 22. Carbon E is 14. And so when dealing with alkenes, we don't see an unusual drop on the adjacent carbon. So we could use the score system to rank them. But for alkynes, watch out for it. Let's work on this example. 2-methyl-1-butene has 5 signals with chemical shifts of 12, 22, 31, 109, and 148. Assign a chemical shift to each carbon atom. So let's begin by drawing butene. So we have a double bond on carbon 1. So this is carbon 1, 2, 3, and 4. And there's a methyl group on carbon 2. Now, looking at carbons 1 and 2, let's call this carbon 5 by the way. We know that carbon 1 is going to have a signal between 100 and 150. And the same is true for carbon 2. But carbon 1 is going to have a lower score value because it's at the end of the chain. So carbon 1 is going to be at 109, and the carbon atom that is part of the double bond that is towards the interior of the molecule, that's going to have a higher score value, so this is going to be 148. Now for the other carbon atoms, we need to actually calculate the score value. Carbon 5 is adjacent to a tertiary carbon, so that gives it a score value of 3. Carbon 3 is between a tertiary and a primary, so that gives it a score of 4. And carbon 4 is next to a secondary carbon, giving it a score of 2. So carbon 3 is going to have the highest of the 3 remaining chemical shifts, which is going to be 31. Carbon 5 has the next highest score value of 3, so it's going to have the chemical shift of 22. And the last one, carbon 4, with the lowest score value, that's going to have a chemical shift of 12. And so that's it for this problem. So you could use the score system when dealing with alkenes. Number 9. The carbon-13 NMR spectrum for C8H10 is shown below. Propose a structure for this molecule. So let's begin by calculating the index of hydrogen deficiency. So it's 2n plus 2, where n is the 8 carbons, minus the number of hydrogen atoms, which is 10, divided by 2. Now 2 times 8 is 16. 16 plus 2 is 18. 18 minus 10 is 8. And 8 divided by 2 is 4. So the IHD is 4. Now looking at the signals that we see here, it's between 100 and 150. So we have two possibilities. Either we have an alkene functional group, or we have a benzene ring. Now, a benzene ring with 3 double bonds and 1 ring has an IHD of 4. An alkene has an IHD of 1. So this could be a benzene ring, or it can be a molecule with 4 double bonds. Which one do you think makes sense? Well, let's draw a structure with 8 carbons and 4 double bonds. So this would be 1, 2, 3, 4. This particular structure will not give us 3 signals. This would show up as signal 1, 2, 3, 4, and that's not including cis and trans effects. Now, if we attempt to, let's say, branch it off, which we could, this still won't give us the answer that we need. So this would be 1, 2, 3, 4, 5, 6. Now we could have some double bonds and a ring. That's another possibility. For instance, we could have a ring and 2 double bonds, and perhaps another double bond outside of the ring. So right now we have a total of 7 carbons. We need 1 more. And if we count, let's say, the number of signals, these two are identical. And then it's 3, 4, 5, 6. So that's not going to work either. What if we were to do something like this? And let's say we have another ring. So this is 6 carbons, 7, 8. So that's not going to work. What about this one? This has an IHD of 4. The structure, 3. The structure on the right has an IHD of 4. And this has a total of, that's 7 carbons. So we got to put a methyl group somewhere. Automatically, that's not going to give us 3 signals. This is going to be 1, 2, 3, 4. And then, let's see, 5, 6, 7, 8. When in doubt, the best structure to draw when having an IHD of 4 or more is the benzene ring, because this is going to be the most common structure that you're probably likely to encounter. Besides that, if it's something else, you'll need other forms of spectroscopy to basically pinpoint what it might be. So here we have a total of 8 carbons. This is orthoxylene. Here's another possibility. We could have ethylbenzene. So this has an IHD of 4 with 8 carbons. Another possibility is paraxylene. And another one could be metaxylene. So these all have 8 carbons, 10 hydrogen atoms. Now let's count the number of signals. So this is going to be 1, 2, 3, and 4. So you can see the line of symmetry here. For the next one, this is going to be 1, 2, 3, 4, 5, 6. And then these two are identical. Here's the line of symmetry. This is carbon 2, and then carbon 3. So this is the one that's going to work. Now if we look at the last one, this is 1, 2, 3, 4, and 5. The line of symmetry is right down the middle. So this is going to be our answer. So let's redraw this molecule, but sideways. So let's call this carbon A, and then B, and carbon C. So clearly carbon A has to be the signal at 21. That's typical of a methyl group. Now what about carbons B and C? Notice that there's 4 signals that corresponds to carbon C, but only 2 correspond to carbon B. So carbon C has to be the 129 signal. Carbon B has to be the 135 signal. And so height plays an important role here. So this is 129, and this is going to be at 135. And so that's how you could use mass spectroscopy. I mean, not mass spectroscopy, but carbon-13 spectroscopy when dealing with benzene rings. Just know that the signals will be somewhere between 100 and 150. And the ones that are chemically equivalent, the more carbon atoms that are chemically equivalent will show up as a peak that's taller than the other ones. So keep that in mind. And then the last thing you need to use is the number of signals to distinguish one structure from another. Now let's focus on the carbonyl groups. The chemical shift for this functional group varies between 150 and 220. Now let's start with the ketones. Ketones have a higher chemical shift than the aldehydes in C-13 NMR, and this is higher than the carboxylic acids, which are higher than the ester functional group. And esters and amides, they're around the same range. So for a ketone, it's usually around 205 to 220. For an aldehyde, 190 to 205. For carboxylic acid, it's usually between 175 and 185. And for ester and an amide, it's between 165 and 175. Now let me give you some examples of some numbers that you might encounter. So here is butanol, and the chemical shift of the carbon in the carbonyl group is 209 for this ketone. Next we have an aldehyde. This is butanol, and the chemical shift for the carbon of this particular aldehyde is 203. In this example, we have propanoic acid, and the chemical shift of the carbon is 181. And for this example, it's going to be an ester. So this is isopropyl ethanoate, and it has a chemical shift of 170. Now, something interesting happens if you attach, let's say, a benzene ring to these functional groups. So if we have a benzene ring attached to, let's say, a ketone, so this is acetophenone, notice what happens. The chemical shift decreases from 209 to about 198. And it makes sense because let's say if you put a carbon atom next to an electron withdrawn group, the chemical shift will go up. But if you put it next to an electron donating group, it's expected that the chemical shift should go down. And the benzene ring can donate electron density to the carbonyl group, giving us a resonance structure that looks like this. And so due to the resonance effect, we can see why the chemical shift decreases. Now the next one we're going to talk about is benzaldehyde. The chemical shift for this molecule will also decrease. And so it's going to be 192. So in most cases, we can see that there's a drop in the chemical shift approximately about 10. Now this one is going to be benzoic acid. And the chemical shift of the carbonyl group is 172. And the last one is going to be an ester. And I'm running out of space here. And the chemical shift for this one, it's not that low, but it's 167. So it's a little bit lower than what we see here. So if you add an electron donating group to a carbonyl group, it's expected that the chemical shift should decrease slightly. Number 10. The carbon-13 NMR spectrums for two constitutional isomers of C4H8O2 are shown below. Identify the functional groups corresponding to each spectrum. So as always, let's begin with the IHD. So it's 2n plus 2, where n is 4 in this example, minus the number of hydrogen atoms, which is 8, divided by 2. Now 2 times 4 is 8, and so that's going to cancel with this 8. And so it's going to be 2 over 2, which is 1. So this either is one double bond or a ring. Now in both cases, we see a signal between 150 and 220. So that's going to be the carbonyl functional group. And so that's going to be our double bond in this situation. Now we don't have any alkenes or any benzene rings. So therefore, the carbonyl groups won't be shifted down by 10, as we saw if we attached them to a benzene ring in the last example. Now, for us to have, let's say, a ketone, the signal is usually around 210. For an aldehyde, it's close to 200. The signal at 180, this indicates a carboxylic acid. And the signal at 170, this is likely to be the ester. Notice that we have a signal at 60. So this is the CO bond of the ester, but we don't see that for a carboxylic acid. Now let's talk about why, because the carboxylic acid does have a CO bond. So why don't we see a signal between 50 and 100 for the CO bond of a carboxylic acid? What would you say? For an ester, notice that there's two CO bonds. This is the one that appears at 60, and for this one, this is part of the carbonyl system. Even though it has a CO bond, because it's attached to the carbonyl group, this is the signal that we see at 171. In the case of a carboxylic acid, this carbon is going to appear at 181. This CO bond is not really relevant because that same carbon is still part of the carbonyl group. And so this is one way in which you can distinguish a carboxylic acid from an ester. An ester will have the signal at 170 and the CO signal between 50 and 100. whereas the carboxylic acid, it's not going to have the CO signal between 50 and 100. Now, the spectrum on the left corresponds to butanoic acid. So this carbon has a signal of 181. The next one adjacent to it is 36. The beta carbon is 18, and the gamma carbon is 14. In the case of the ester, this corresponds to ethyl acetate. The carbonyl carbon has a chemical shift of 171, and this carbon here, that's the CO bond of the ester, that corresponds to 60. The methyl group on the right is 14, and the methyl group on the left is 21. Now, the examples that we've seen before, all of the spectrums that we've considered were based on this mode, broadband decoupled. All of the signals appeared as singlets. But there's another mode that you need to be familiar with, and that is the proton-coupled mode of C-13 NMR. And in this case, you're going to see splitting not from the adjacent hydrogens, but the hydrogens that are directly attached to the carbon. They will split those carbon signals into triplets, doublets, and quartets. Let's call this carbon A, B, C, and D. Carbon B is the signal at 69. Carbon A is the signal at 23. And carbon C is the signal at 32. D is 10. Now, what type of splitting pattern are we going to see for carbon 3? In H-NMR, we would look at the adjacent hydrogens. But for proton-coupled C-13 NMR, we're not going to look at the adjacent hydrogens. To analyze carbon B, we're going to use the hydrogen atoms that are directly attached to this particular carbon. So what is the splitting pattern that we see here for carbon A? Will carbon A show up as a singlet, doublet, triplet, or quartet? Now carbon A has 3 protons, and so using the n+1 rule, 3 plus 1 is 4. So therefore carbon A will appear as a quartet. So carbon A is at 23, and so let's draw a quartet in this region. Now keep in mind, you could draw it like this if you want to. Now moving on to carbon B. Carbon B only has 1 proton on it. So 1 plus 1 is 2. This is going to appear as a doublet. And so that's at 69. So let's draw a doublet at 69. Or you can draw it this way. Now carbon C has 2 protons. It's a methylene group. 2 plus 1 is 3. And so this is going to appear as a triplet at 32. So we can draw it like this, or like that. Now the last one is a methyl group. 3 plus 1 is 4. So this is going to be another quartet. And that's at a signal of 10. So it's going to look like that. Number 11. The proton-coupled C-13 NMR spectrum for C6H12O is shown below. Propose a structure for this molecule. So as always, let's begin with the IHD calculations. So it's going to be 2 times 6 plus 2 minus the 12 hydrogen atoms divided by 2. 2 times 6 is 12. And so that's going to cancel with negative 12. And thus we're going to get an IHD of 1, which means we could have 1 double bond or 1 ring. Now the double bond is going to be a carbonyl group because we see a signal close to 210. And that's usually the signal for a ketone. Now this is going to appear as a singlet. So we got the multiplicity for the signals as well. This is a triplet, quartet, doublet, and a septet. So with that in mind, what do you think the structure is going to be? Now for the triplet, this corresponds to a methylene group because 2 plus 1 is 3. For the quartet, this corresponds to a methyl group. 3 plus 1 is 4. For the doublet, this corresponds to a methine group. 1 plus 1 is 2. And for the septet, this is going to be 2 methyl groups that are attached to the same carbon atom. Because 6 plus 1 is 7. So let's see if we can put all of this together. What type of group do we have here? Will it be a CH, CH2, CH3, or just a C? Now it can't be a CH3 because methyl groups always exist at the end of a structure. It can't be a CH2 because then we would only have a total of 3 carbons. It's either a C or a CH. Now we have a total of 6 carbons. So using that, how can we tell if this is going to be a C or a CH? Well, here's the first carbon. Here is the second, third, fourth, and then these two would add up to 6. So we don't have any C's in our graph, in our spectrum. There's no missing carbons that we didn't account for. So this has to be the CH. It can't be anything else. So we're going to make this the right side of the molecule. Okay, what just happened? This computer's acting weird. So we're going to have a CH attached to 2 methyl groups. So we used up this signal and the septet. Now we still have another methyl group to put in this molecule somewhere. And we're going to put that on the left side. Let's put it over here. Since methyl groups always exist at the end of a molecule. Now the only 2 other things we need to put into this equation is the methylene group and the carbonyl group. So one possibility is to write it out like this. The other possibility is to put the methyl group and then the carbonyl group, followed by the methylene group and the isopropyl group. So those are the 2 ways in which we can connect all the groups that we have here based on the spectrum. So now let's put down the signals that we have. The signal for the carbonyl group is 209. And for the septet, that's around 23. So that's the 2 methyl groups that are equivalent to each other. And we can see that because the peak is tall, it indicates that there's 2 or more equivalent carbons that correspond to that signal. Now the doublet, that's around 25. So that's going to be the CH carbon. And the triplet has to be the methylene carbon. So that's going to be at 53. And the quartet is the methyl carbon, which is at 30. So for this molecule, the numbers will be the same. Now let's use the score system to see which of these 2 structures is more consistent with the spectrum. So let's calculate the score value of the methylene group. So this is a primary carbon, this is a secondary carbon. So we're going to give this a score value of 3. And for this one, the methyl group, it's next to a secondary carbon. So we're going to give it a score value of 2. Now for the methine group, it's adjacent to 2 primary carbons and a secondary carbon. So we're going to give it a score value of 4. So notice that the methyl group has a higher score value but a lower chemical shift compared to the methylene group. I mean, this is a methine group. I called it a methyl group. But the CH group it has a lower chemical shift of 25 compared to the CH2 group, which is 53. And they're both one carbon away from the carbonyl group. And this has a higher score value. So it doesn't make sense that the methylene group will have a higher chemical shift. Therefore, this structure is not consistent with the score system. Now let's look at this structure. The methyl group here still has a score value of 2. That's not going to change. Now the methylene group is adjacent to a secondary carbon and a tertiary carbon, giving it a score value of 5. The methine group is next to a primary, and a secondary, giving it a score value of 4. So now we can see why the methylene group is much higher than the methine group. For one reason, this is next to the carbonyl group and the methine group is not. So that's one reason why this is higher than this one. The second reason is that it has a higher score. So there's two factors favoring the high chemical shift of the CH2 group. And if we compare these two, clearly this has a higher score value, even though these two groups are one carbon away from the carbonyl group. This has a score value of 5, this one has a score value of 2, and so we can see why the CH2's chemical shift is much higher than the methyl's chemical shift. So this structure is most consistent with the data that we see in the spectrum above. And so it turns out that this is indeed the answer. Now the last thing that I want to discuss in this video is something called DEPT C-13 NMR Spectroscopy. DEPT, D-E-P-T, stands for Distortionless Enhancement by Polarization Transfer. Now what you need to know is that if the excitation angle is at 0 degrees, this is basically the same as a broadband decoupled C-13 NMR spectrum, where you'll see all the signals. You'll see the carbons, the CHs, the methylene groups, and the methyl groups. Now, if the angle is at 45 degrees, you'll see the methine groups, the methylene groups, the methyl groups, but you won't see any quaternary carbons. Now, if the angle is at 90, the only groups that you'll see are the methine groups. If the angle is at 135, the methine groups and the methyl groups, they will have a positive polarity, which means that the signal will be above the x-axis. The methylene groups will have basically a negative polarization, and so the signal will appear below the x-axis. So this is what you need to keep in mind when dealing with DEPT C-13 NMR spectroscopy. Number 12. The DEPT C-13 NMR spectrum for C7H14O2 is shown below. Propose a structure for this molecule. What we need to do is determine which signals correspond to a CH3 carbon, a CH2 carbon, a CH carbon, or a C carbon. Now, we know this corresponds to a carbonyl group. Now, it can't be an aldehyde, because an aldehyde would show up around 200, so it's not a CH carbonyl group. It's just a C carbonyl group. Now, for 135, notice that we got these two peaks that are below the x-axis. And so these will correspond to the methylene CH2 group. Now, 90 only shows the CH carbons, which means that the signal at 67 corresponds to a CH carbon. So these other two signals here have to be methyl groups because they're not present at the 90-degree excitation angle. So at this point, we've identified all the peaks that we see here. Now there's one more thing that we need to mention. That is the signal at 67. Between 50 and 100, we know it could be a CO bond, like an ether, an ester, or it can be an alcohol, or the signal at 67 could be an alkyne. So we need to calculate the IHD to eliminate some possibilities. So it's going to be 2n plus 2, where n is 7, and there's 14 hydrogen atoms, divided by 2. 2 times 7 is 14, which cancels with the negative 14 on the right. And so we have 2 divided by 2 left over, giving us an IHD of 1. So we have either one double bond or one ring. And automatically we see that we already have a double bond here. So there's no room for a triple bond, which means this has to correspond to a CO signal. So we could have an ester, or we could have a ketone and an ether. But the signal at 173 is not consistent for ketones. Ketones exist around 210. So this must be the carbonyl group of an ester. And we know it's not a carboxylic acid because the carboxylic acid won't have a CO signal at 67. It'll only have the carbonyl group, typically around 180. So this indicates that we have an ester functional group. Now automatically we know that the CH has to be attached to the oxygen. And what else do we know? Now we have 2 methylene groups, and we have 2 different types of methyl groups. So the methyl groups will be at the end. But notice that the signal at 22 is much higher than the signal at 14. So one of the methyl groups will be an isopropyl group. So this has to correspond to 2 methyl groups. And the reason why we could say that is, notice that we have a total of 7 carbons in this structure, but we only have 6 signals. So that means 2 carbon atoms have to be equivalent. So this indicates that we have an isopropyl group, which is usually attached to a CH carbon. So far, we've considered the carbonyl group, the CH carbon, the methyl group with the one that has the tallest peak. And so left over we have 2 methylene groups and another methyl group. Now the other methyl group has to be at the end. Methylene groups exist in the middle of a chain without any additional branching. And so the structure has to be this. So the carbonyl group is the one with the signal at 173, the CH group at 67, the 2 methyl groups at 22, and then this methylene group next to the carbonyl group must be this signal here, which is at 37. The other one is at 19, and the other methyl group is 14. And so that's basically it for this problem. This structure here is the answer. Thanks for watching.